This is Lab 2, Motion of a Free-Falling Object. So the purpose of this lab is to examine the motion of a flat free-falling object and measure the impact of drag force on the free-falling object by comparing the measured data to computational data. The principles we'll be using is Newton's second law in drag force. And for a little preview, due to the drag force, the predicted position of the folder will be less than what is expected. The system is the folder, and the surroundings are the drag force and the gravitational force from Earth. So the principles used, first, drag force. It's a force that opposes a gravitational force. It makes an object fall a little slower, and it can be modeled by negative v times v squared plus or times v hat. And then Newton's second law states that the net force acting on an object is equal to the change in momentum divided by the change in time. And with Newton's second law, we can derive these two equations, the position update and the velocity update. And we will be using both of those in the tracker data since the force is not constant. So here's the measured data from tracker. I dropped a folder from rest straight downwards, and as you see, we get this nice curved line here. And this is just some of the data from tracker. The important parts, the frame rate was 0.033 seconds a frame, so that will be our delta t. This is our initial position, so we'll be putting that into glow script as the initial position. And then the end time was 0.533, so that will be the loop until time in the code. So first, our predicted data with no drag force. As you can see, I updated the position vector, I changed the mass, changed delta t to that 1/30 that we got earlier. B is 0 since there's no drag force. And then until 0.533, which was our end time, just going to keep updating the velocity and updating the position, and we get this graph here. So with drag force, with some trial and error, I got that B was 0.052. Then going down here, it's mostly the same, except now we have this drag force that we have to account for. So that's the equation for that. And then all I did was added that into my FNet. Then when we compare all of the graphs together, we see that measured is on top and drag is a little below it, but overall pretty accurately describes where it is. And predicted with no drag stays pretty similar for about 0.3 seconds. But then after that, it just drops off a lot from the other two and predicts that it's going to go way farther than it does. And obviously that's because there's no drag force, so it thinks that it'll fall faster than it actually is. So some sources of error, the folder may not have been dropped with an initial velocity. There may have been a slight downward initial velocity, thus making the folder travel faster than it should have. And the center could have been wrong on each frame, since it is kind of hard to find the exact center. So the position may be slightly off too on each data point. So some additional questions. The velocity versus time graph for the predicted position with drag force predicts a terminal velocity. A terminal velocity occurs when the curve levels out and the slope becomes 0. As seen in the drag force graph, this happens near the bottom of the larger graph. So that's about right here. We can see it start to level off. And then what if the folder would reach a terminal velocity sooner if it had initial downward velocity? And if we gave the object an initial velocity of 0, -5, 0, we now have the smaller graph. So as you see, it starts leveling out much sooner. It's around 0.3 here, and really like 0.4, 0.45 without it. So it would hit terminal velocity sooner if it had an initial downward velocity.